In this section, we are going to start talking about the graph data structure. And graphs are an important data structure for us to understand because it allows us to begin implementing in algorithms such as the Dijkstra algorithm, breadth first search, and depth first search, which we will see in the coming sections. But for us to be able to understand how graphs work, there is some terminology that we need to first go over, such as what the vertices are and what edges are. So if we create a simple graph, we have nodes as such. And so these are going to be our vertices. So our vertices can also be just called nodes. And so what edges are going to do is they're going to connect the vertices. So we can have an edge, and we'll give these labels A, B, C, and D. So we can have an edge going from A to B, from B to D, from D to A, and from A to C. So all of these are our edges, and I'll label them E for edge. So you can see where this might be useful for us in a real world scenario. So assume that our vertices here is a city, and then we have an edge, and it's a road. So we have a bunch of cities, and we have a bunch of edges, aka roads. So if these are our roads, and these are our cities, so we'll say C, C, and C, and then R, 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 and R for our roads. Well, now we can create or use an algorithm to figure out the quickest way to get from this node or this city to this city, because this road and this road might have more traffic than taking these three roads. So that's just one use case for a graph, right? So think of it as cities, and then you take the edge, aka the road, to get to the next city, and so on and so forth until you're able to hit your desired destination. So we have some additional terminology that we can go over. And what we have is we have adjacent vertices, and this is what connects the nodes. So a direct edge. Between the nodes, aka the vertices. We have the degree of a node, and this is the number of edges going to a vertex. So in this city node up here, the degree would be 2 because we have 2 edges going into this city. We have the path, and this is how to get from one node to another. Oh, there we go. How to get from one node to another. We have our connected graph, and this is the path. This means that our graph has a path between every two nodes. And we also have a complete graph. And this means that there is a direct edge between any two vertex. So if we created a very simple graph with three nodes, and we did this would be a connected graph because we have a path between every two vertices. We can get from any vertex here to another vertex. And then if we added in this edge, well, we now have a complete graph because we have a direct edge between any two vertices. So in this case, we can any node can get to any other vertex directly. So that is what a complete graph is. So now we have different types of graph. And there's quite a number types of graphs that we can talk about. And we have an undirected graph. And undirected means that you can go from one node to another, and it's always both ways. We have a directed graph, and in this case, only the A node can go to the B node. So, in here, the edge only goes from node A to B. Right? So that's the difference here between our undirected and our directed. And the undirected, we can go either from A to B or B to A. But as soon as we have a directed, we can only go, in this case, from A to B. We cannot go from B to A. We also have an unweighted graph. So that means we can go from A, I don't want to have a directed, we can go from A to B to C, and there are no weights associated with any of these edges. So you can imagine a weighted graph is the counterpart to this. And if we have A, B, C, and this is still an undirected graph, we can have a weight of 5, and we can have a weight of 3. So from A to B, it's going to cost us 5, and from B to C, it'll cost us 3. So an easy way to think of this is think of weights as distance or time. So if we go back to using a city for an example, so we have city A, city B, city C, and we'll say city D, but we have, let's say, 6, 3, 2, and let's add 1 here, and we'll say that this is 1. Well, for us to get from A to D, let's change it from 1. Let's make it 5. Just that way it's not as obvious. For us to get to A to D here, we would go from A to C, so A to C, where our weight is equal to 5, and then we would go from C to D, where our weight equals 2. So our total weight for that path would be 7. Whereas if we went A, B, C to D, then we would have 6 plus 3 plus 2, obviously, which is 9. So that would not be the most efficient path for us to take, in this case, to get from A to D. So think of that back to the going from city to city. You could think of these weights as how much traffic there may be. So how much time it'll take if we go a certain route. So we want to find, obviously, the most optimal path, which we can do using algorithms such as Dijkstra's or breadth first and depth first. So the last thing that we can do is how we can represent a graph data structure. And what I'm going to do is use an adjacency matrix to represent our nodes and our edges. So let's imagine that we have A, B, C, and D for our nodes. So what we can do is we can create a matrix A, B, C, and D, and then we can also have A, B, C, and D here, and inside we create our matrix. And that was not what I wanted to do. So in here we're creating our matrix. And so that we can visually represent this, let's do A, B, C, and D, and we'll create our graph from above. So we see that we go from A to B, so we can put a 1, and we go from A to C, so we put a 1, and since there's not a path from A to A, meaning this is what that would look like, so we don't have that. So now we can go to the B node. We see we connect from B to A, and also from B to C. C connects to B, and C connects to D, and then D only connects to C. And this is an example of an unweighted, undirected graph. And this is how we were able to represent this very simply with what nodes connect to what other nodes via the edges. So our representation in here is our edge, if it exists or not. Otherwise, everything can be initialized to 0 to indicate that there are no edges between those two nodes. So now that we have a good understanding of how graphs work and how we can represent a graph, we will begin implementing in our own graph in the next lecture. And if you have any questions at any point, please feel free to ask them in the Q&A section. In this lecture, we are going to begin implementing in our graph. And since we talked about different graphs in the previous lecture, we are also going to implement in a directed graph and an undirected graph. And both of our graphs are going to be weighted. So, since we are going to implement in two graphs, directed and undirected, it would make sense to have two separate structs, directed graph and an undirected graph. Inside of our directed graph, if you recall in the previous lecture, I said that we were going to use adjacency matrix. So that's what we will call our field inside of here, adjacency. There we go, matrix. And what we're going to do is we're going to use a hash map that is going to have a string and also a vector that contains a string and an I32 tuple. And we're going to use a hash map, and a hash map is a data structure that uses a hashing function to map identifying values known as keys. So the key in our hash map is going to be the string, which is going to be the node or the vertex, and it's going to map it to their associated values, which is going to be our vector of a string and an i32, where the string is another vertex and the i32 is the weight of the edge. And hash maps are, so you can see that they're allowing this object to be associated to our vector here, which is going to contain the other nodes and edges that our node here connects to. And a hash map has extremely fast lookup, so obviously this is going to play very nicely with when we add nodes and also create edges on our vertexes or our vertices. So we'll take this and we'll also plop this down here for our undirected, and since we are using a hash map, we need to bring into scope the hash map. Alright, and now what we can do, and since both graphs, undirected and directed, are very similar, the only difference is one, you have to look to see if one node can actually go to the other node, and the other, which is a directed, and the other, which is in this case is undirected, is as long as there's an edge between two nodes, they can go either way. So there's a very slight difference, and with this we can implement our methods in using a trait. That way we're not doing two completely separate implementations for each graph. So we know that each graph is going to need a new method so that we can create either a directed or an undirected graph. And then we also are going to have a method that allows us to retrieve a mutable reference to our adjacency matrix value inside of our struct. So we will say and mutable self, and we will return a mutable reference hash map string with a vector that contains our string and our i32. And close it out. Alright, so that looks good. And now we can actually add some logic to some of our methods. So we both know each graph is going to need to be able to add a node. So we will say add node. And with us adding a node, we know that we're changing a field. So we have a mutable reference to ourself. And we're going to add our node, which is going to be a string. And in this case, we'll return a Boolean. That way we know if our node was successfully added or not. Well, we want to make sure that our node doesn't already exist in our adjacency matrix. So we can match on our adjacency matrix, and we're going to get our adjacency matrix by calling our method here. And we will say get, which is a hash map method available to us, and we will get our node, aka so our key. So we're looking for this node inside of one of these hash maps here, depending on if it's directed or undirected. So if the node doesn't exist, well, that's good. That means we can add it. So we can say self.adjacency matrix dot insert. We want to dereference the node, call it to string, and we need to give it a vector when we add it in. That way when we go to add in edges, we have a vector where we can connect the additional node with its weighted edge. And upon that being added successfully, we want to add true. And in the case that we cannot add, which is any other case, then we want to return false. So let's make sure that everything is still building properly. So we will say cargo build, and it's because I need an S there. Alright, so we are compiling correctly, so everything looks good to go so far. So now we want to be able to add edges. That way we can start connecting different nodes together. So we will create add edge here, and since we are going to modify the vector in our hash map, again, we're going to have a mutable reference to ourself, and we're going to pass in an edge, which is going to contain a tuple with a string slice, and an I32. So these two string slices are going to represent the two nodes that we are trying to connect, and this I32 is going to represent the edge, at the edge's weight between the two nodes. So what we can do here is, first off, we need to make sure that the node that we are trying to connect to exists. So we can say add node to edge.0, so add a node for this edge and add a node for this edge. And remember, we can do that because if that node already exists, then we just return false, so no harm was done. Otherwise, we are going to add in this node here. That way we're not adding an edge to something that doesn't exist. So now that we have confirmed that both of our nodes that we are trying to have an edge between exist, we can begin adding in our edge. So we can say get our adjacency matrix. We want to get the entry, and entry is a hash map method available to us where we get the entry for this node. So we are literally going into the hash map and getting all the information associated with this node. And so we want it to be toString, and then we're going to modify it, and we'll pass in a closure where we modify accordingly by pushing in, and we are pushing into our vector, and we are pushing in the edge.1, so this node, and we're going to have to turn it to a string because that is what our vector wants. toString, and we need to give it the weight, and edge 2 is here, so remember 0, 1, 2. So what we are doing is connecting edge 0 to edge 1 with the weight edge 2. And let's run cargo format to make this look nice. Alright, so again, we're getting our entry for the node that we are wanting to connect an edge to, so edge 0. We want it to connect to edge 1, so we take that entry, we modify it, and we're pushing in to the vector the edge 1 and our weight, which is this right here. So we are pushing in, hey, edge 0 is going to connect to edge 1 with the weight edge 2. And that's all we need to do for adding an edge. So we can now implement an additional method called neighbors. And our neighbors is going to return a result because we want to see if there's any neighbors, because there might not be, and we want to have a vector, and our vector is what contains all the neighbors to our node, because remember, we're pushing in when we add in a new edge, which therefore means that we're going to have a new neighbor. So we can just return the vector, and we also need to return maybe a custom air type here, because what if we want the neighbor of a node that doesn't exist? So something here like our custom air type of node not in graph seems to make pretty good sense to me. So what we can do here is actually create ourselves a new custom air type, and so we'll give it a derive debug. That way we can print it out if we need to, and we will say node not in graph, and this is going to be our custom air type if a node does not exist. So now if we pass in a node that doesn't exist, we will get back our custom air type of node not in graph. So I feel like that's a pretty safe thing to do, to ensure that, hey, when we return an error, if the node doesn't exist, we know why that error was returned. So what we can do is say match self dot adjacency matrix. So we want to get our adjacency matrix, and then we want to get the node. So if that node does not exist, then we want to return our error of our node not in graph. Otherwise, if that node does exist, that's great, because all we have to do now is return our OK with that value inside. And that value inside is going to be our vector of our strings and our weights. So we're returning back a reference to our vector, and that vector is going to contain all the nodes and all the weighted edges that are associated with that node. So that is all we need to do to get all of our neighbors for our graph. So it looks like all of our trait methods are indeed good to go. So let's begin implementing in our trait for our directed and undirected graph. So we can say impl graph for directed graph, and we will say fn new, and here we want to return a directed graph, and so we say directed graph, and we have our adjacency matrix, and obviously we need a new hash map. So that looks pretty good. And then the other thing that we need to implement just for our directed graph is our adjacency matrix. In here we are returning a mutable reference to our hash map of a string with a vector that contains a string i32 tuple. And so here we just want to return a mutable reference to our self dot adjacency matrix. So that's all we need to do for our for our directed graph. So now we need to impl graph for undirected graph, implement new again, and this time we are returning an undirected graph, where here we need to have our undirected graph that returns an undirected graph with a new hash map. And again, we need to create our adjacency matrix, which is a mutable reference to ourself, and mute hash map string vec string i32, and now we want to return a mutable reference to ourself dot adjacency matrix. Alright, so let's make sure we don't have any compiler errors, and we're good to go. And let's do a cargo format to make sure everything looks good. Awesome. So there is actually one more method that we need to implement ourselves for our undirected graph. And I want to take a look at this method right here that we implemented in on our trait called add edge. So if we look at this again, we see that we are making sure that our node exists, that we are trying to add an edge between for both nodes, and that way we know for a fact that, hey, both of these nodes are in our adjacency table, or excuse me, our adjacency matrix. So what we're doing is we're connecting edge 0 to edge 1 with this weighted value here. So if you take a second to kind of think about that, and again, I'll say it again, we're going from 0 to 1 with this weight. Well, that means that we did the directed graphs implementation here for add edge. But what about undirected, right? Because we also need edge 1 to go to edge 0. So we need to specify that, hey, this edge goes both ways. Because currently this edge is only going to go from 0 to 1. So from 0 to 1. So from, node A to node B. But currently it does not go from B to A. So what I want you to do is I want you to add in the implementation for add edge, and our function setup will look the same as it did in our trait, and we need to have a string slice I32, and we can actually copy in the rest, or copy in what we did above. So we were making sure both of our nodes are here before we try to add an edge. And now we are going to add our edge between this vertex and this vertex. So we are getting our adjacency matrix dot entry edge dot 0 dot toString. Now we want to modify it, pass in via closure our value that we returned, and we want to push in edge.1.2 string and then our weight, so edge.2. Alright, let's cargo format this to make it pretty. Alright, so as you can see, everything is the exact same as what we did above. So what I want you to do now as a small little assignment is I want you to add in connecting edge.1 to edge.0 so that the graph is now undirected, right? Because if we go from 0 to 1, but also from 1 to 0, so from this vertex to this vertex, and then go this vertex to this vertex, then it's technically undirected. So I want you to take a minute to try and implement this in yourself, and we'll go over my implementation in the next lecture, and we will also begin implementing in our test cases in the next lecture so that we can test out our graph to make sure it is functioning properly. So I will see you in the next lecture. Alright, in this lecture we are going to go over the solution to the little assignment that I assigned at the end of the previous lecture, and then we are going to begin implementing our test cases for our directed and undirected graph. So let's go ahead and add in the solution for the previous little assignment. And hopefully that you noticed that it was not too bad, and all we had to do was add in an edge from 1 to 0 instead of 0 to 1. So we will say edge 1 dot toString, and then we want to modify it, and we will modify our value that we get, and we will say e dot push edge 1 dot toString. Excuse me, not 1. We want to go from 1 to 0, and we need to obviously pass in the same weight, so we still say edge dot 2. So let's format this to make sure it looks good. So we're going from 0 to 1 and 1 to 0 here. So we're just reversing our edge and saying, hey, it is going both ways. And that's all we have to do for that portion. So let's build, make sure we don't have any little errors. Alrighty, so everything's looking good there. So what we could do now is start implementing in some of our test cases. So let's come down here and say config test, and we will say mod test undirected graph, and we will say use super, and we'll just bring them all into scope to keep it easy. So now we are saying that we have a test. Let me put in my brackets, and we want to test out our neighbors, and this will let us pretty much test everything that we need to test by doing this. So we will say let mute graph equals undirected graph new. So this is going to test out our new. Now we want to add edges, and we will say we're going to have A, B, and we'll give it a weight of 5. We will do another edge. We will say B, C, and give it a weight of 10. And graph, add edge again, and we will say C, A, and I missed a quotation, so we need to add that in. Alright. Let's make sure there's not, okay. Alright. So now we can assert equals. And so with us doing add edge, if we look at add edge, we're actually testing out add node as well. So this covers all of our methods that we created. So we want to assert equals that are graph.neighbors of A, and we want to unwrap the value, that way we can look inside, and we want to say make sure that it references a vector that has a string from B, has a weight of 5, and we also have a string from C that has a weight of 7. And it looks like I need you there. There we go. Alright. So let's cargo format this, make sure everything, okay, there we go. So yeah, that looks pretty good. So we're seeing what neighbors A has in an undirected graph. So A will have a neighbor of B, and then A will also, since we're here, have a neighbor of C. So if we run cargo test, we supplied 3 arguments. We need to add in parentheses everywhere here, since we are needing to add in a tuple. There we go. So now let's run it. And our tests passed successfully. So all of our methods for our undirected graph looked pretty good. So what we can do now is test out our directed graph. So what we'll do is we'll create one more here. We need to specify that it is a test, and we will say test, and we'll call this one directed. And it's going to be set up pretty similar, so we will say let mute graph equals directed graph new, and we will say graph dot add edge from A to B with the weight of 5, and we'll just go ahead and copy in these other two, that way we're not wasting time typing it. And we'll actually add one more edge here just to make it a little different, and we will say from B to A with the weight of 5. So we made this edge go both ways. Alright, so let's assert equals here to test out that our graph dot neighbors of A, we need to unwrap the value here, and let's say a reference to a vector that contains a string from B with a weight of 5. Right, that should be our only neighbor for A, because we're going from A to B, and this will let us check to make sure that our directed graph is indeed directed, because we should not see a neighbor of C. So let's format this to make it pretty. Alright, so let's run this test now to make sure that it returns true as well. Test directed, returned OK. So we are looking good there. Let's add in one more test case here, and let's do it from a graph where we check the neighbors of B. And then we need to unwrap our value here. So with it being B, we should see C and A returned. So we want to return a vector string from C, which has the weight of 10. Oh, I need to add in the parentheses here. There we go. And we need a string from A where we have 5. And that looks good. Let's cargo format it to make sure. Alright, and let's run our test, and we still see that everything is passing successfully. So our graph implementation looks good to go. We are passing all of our test cases, and our test cases are indeed testing our add edge on our undirected and our directed, as well as our neighbors, and adding in a node. So if you have any questions about a graph, please feel free to ask me in the Q&A section, and we will take this knowledge of our graphs and begin implementing in some algorithms such as Dijkstra. So we have some algorithms to go over starting in the next lecture. So We'll look forward to seeing you there. And again, if you have any questions about what we did with our graph implementation, please ask them in the Q&A section.